Hello, everybody. Welcome to the first class of the semester. We're going to jump right on in, and we're going to talk about inductive and deductive reasoning. This is section 1.1 of our book, so you can open up the textbook or the e-text if you'd like and follow along. I'm mostly just going to kind of work through some examples. I'm a big fan of sort of teaching through examples and letting you guys really just see it. Rather than just reading some definitions and whatnot. Let's go ahead and start off, though, with some definitions, but I'm going to sort of simplify them, make them a little easier to understand. So the book will define inductive reasoning as the process of reasoning that arrives at a general conclusion based on the observation of specific examples. And I hear that and I go, yikes, that's pretty annoying. That it's hard to parse through. There's a lot of big words and it's just weird. So basically what I like to do is turn this into something a little easier. Inductive reasoning is just finding a pattern and using that pattern to figure out what the next thing is. So we could start off with a good example here, and I could just give you a bunch of numbers in a row, and these seemingly have no pattern. There's no rhyme or reason to them, but if we look carefully, we'll notice what's actually going on. So let's go ahead and look here. I go from 1 to 1, and then I go from 1 to 2, and then I go from 2 to 3, 3 to 5, 5 to 8. And the question here is, what happens next? You know, what are my next numbers that I get? And if you look carefully at this, you should be able to tell that the previous two numbers added together will give me the next number. So if I take 1 and 1, that's going to give me that 2 right there. And then if I take 1 and 2 and I add those, that's going to give me 3. If I take 2 and 3 and I add them, that gives me 5, and I can keep going on. And let's actually do that. Let's keep going on. So if I want to figure out what this number is right here, this first blank, I'm going to take 5 plus 8, because that's the previous two numbers. I'm going to add those together. And that should tell me that this number here should be 13. Now that I have that, I can do 8 plus 13 equals 21, and that's going to give me the next number, right? So I'm just taking these two previous numbers, adding them together, and that's giving me the next number. Lastly, we'll take 13 plus 21, and that's going to give me 34, and I can fill in this last guy here. And this would keep going on, but I'm just asking you for the next three numbers. And so what I've done here is I've used inductive reasoning. You're probably not thinking about it in your head as inductive reasoning. You know, when you do something like this, you're just like, oh, I saw the pattern and I just figured it out. Well, that's exactly what inductive reasoning is. It's that finding a pattern and then just using that down the line. So you do this a lot. You just probably haven't assigned the name inductive reasoning to it. But there's inductive reasoning right there, and a good example. This sequence here, I'll probably talk about this occasionally. This is actually called the Fibonacci sequence. It actually comes up in a lot of places, both in math and in the real world. I definitely recommend doing some Googling of it, and just honestly, there's some really cool pictures that you can look at. So let's move on. I've got that filled in right there, just in case you're not, watching the recording and you're just looking at the lecture slides. So there's our three numbers right there. And let's go ahead and do another example here. So if I take two odd numbers and I add them together, will the result always be an even number? And I want to use inductive reasoning here. And then I'm going to actually talk about why inductive reasoning isn't a great thing to do here. But I'm going to start off with inductive reasoning. Let's just take two odd numbers, 3 and 7. Let's add them together. We get 10, right? Let's take two more odd numbers, 31 and 1. I get 32. Let's do this again. 31 and 1. 31 and 1. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 32. 5, and 17. And I add those together, I get 22. What I'm noticing here is that all of these are even numbers. So it kind of seems like if I take two odd numbers, I always get an even number, right? And what we'd say here is by inductive reasoning, so using this sort of idea of inductive reasoning, two odd numbers added gives us an even number. Now, we're using inductive reasoning here. We used a couple examples. We looked at so we saw that it happens in those examples. We're looking at this pattern. We see it happen a couple times, and we go, boom, I think it happens. Yeah, it seems like it's true. And in fact, it always is true. But who's to say that you couldn't come up with another example where it didn't work? I mean, I've only tried 3 examples here, and obviously there are a lot more odd numbers and combinations of odd numbers that I could use. And so in theory, it's possible that I could add 2 odd numbers and not get an even number. It doesn't seem like it, but in theory, it's possible, right? And here's the idea. When we use inductive reasoning, we don't really know for sure. I mean, I'll tell you now, just sort of as an aside, 2 odd numbers added together is an even number, but we don't really know just by using a couple of examples. Really, what we'd want to do is try every single possible example, but that doesn't really work, right? You have got an infinite amount of numbers. You're not going to sit there forever trying to do this. So that's kind of a fault of inductive reasoning, sort of a part where it fails, if you will. It maybe fails isn't the right word, but it falls a little short of giving us a definitive answer for sure. So again, you'll see this throughout lecture recordings in the course. I have the slides typed up with what the work I just did, just so that you guys can see it if you're not watching the recording. So I'll skip through some of this here. And so in comparison to what I've been talking about with inductive reasoning, where it's not a for sure definitive answer, although it's a pretty good answer, it's a pretty good guess that if I take those 2 odd numbers and I add them, I get an even. It's not definitive, and this is where deductive reasoning comes in. And again, this book has this long, lengthy definition. I'm not really gonna highlight it, other than that this part, it's based on rules. Let's just go to my definition. It's a little bit easier to understand and to follow. Deductive reasoning is using facts or rules to figure out that something has to be true, that it must be true. Okay, so I'm not using a pattern. I'm not using a handful of examples just to try and convince myself that something's true. I'm actually using facts. I'm using factual evidence to show that something is true. Let's go ahead and do this. So if I tell you that a student must be registered for 12 credits to be a full-time student, okay? So that's just a fact. Maybe that's at Front Range, maybe another school. So in order to be full-time, you have to be registered for 12 credits. So then if I go on and I tell you that a student is registered full-time, what do you know about the student? Well, they have to be registered for 12 credits in order to be full-time. So if they're registered full-time, you know that they have to have 12 credits, right? I'll write this down. They must have, and let's say at least 12 credits. They could have more, but they have to have at least 12 credits, right? And this right here is using deductive reasoning. There's no pattern that I'm following. I'm not looking at a handful of students and seeing, oh, he's full-time and he's got 12, and she's full-time and she's got 14. I'm actually just using the fact that a student that's full-time has to be registered for at least 12 credits, right? And so that's me using deductive reasoning. I'm using a fact in order to come up with this statement that the student must have at least 12 credits, okay? So let's go on to another example here. And this one's a really fun one to do with a whole bunch of people standing around you. You ask everybody to pick a number, and I recommend you do this. Pick any number you want. I'm gonna pick the number 5. I'll write it over here. We're gonna multiply that number by 2. So take your number and double it. My number goes to 10. Let's add 6. And I get 16. You'll have something different. I'm gonna divide it by 2. And then I'm going to subtract the original number. And so when I subtract that original number, I go minus 5. That gives me 3. And so the number I have is 3. And so why this is really fun to do with a lot of students, you know, all doing this on their own, is that you have everybody gets the number 3, and it doesn't seem like it. You're like, wait, I picked a different number, right? Like we all had different numbers, but we all got the number 3. So this right here, what we've all done, you know, collectively as a class, that's inductive reasoning. We took a bunch of different people, we all had them pick a different number, and then we all happened to get 3. And so what we're doing is we're using the pattern that we see. We're noticing that every student is getting the same number output, that number 3, regardless of the input. And we're using that pattern to say, well, I think we're going to get 3. That's inductive reasoning. But again, that doesn't necessarily prove it. We want to use deductive reasoning to do that. And so using deductive reasoning is a little bit tougher. It's a little bit more involved because we got to use mathematical facts and rules. But let's go ahead and do this. Let's take a look at the sort of statements that I made, and let's just do it with a number X, right? And so this is just going to be a variable that I use. It's not a predefined number like 7 or 5 or anything like that. It could be anything, and we're just going to do mathematical operations to it. So like I had you start off with, we picked our number, and we're all going to say it's X. And then if you double it, you're going to have 2 times X. We'll call that 2X. We're going to add 6 to whatever we just had. So I take my 2X and I add 6 to it. And then I divide this by 2, right? And now let's be careful here. I'll show this work. 2X plus 6. I could factor out a 2. And that's 2 times X plus 3. So now when I divide by 2, you could just cancel this 2 out front. And that just leaves you with that X plus 3 that we see right there. Then I subtract the original number, and I subtract off an X because that was the original number. That's what we're doing right here. And you notice that you're always left with 3. So what these steps do is they actually prove that you always get 3 using mathematical facts, right? You start off with a general number, X, right? We don't start off with something specific. And that immediately tells us, because we've started with this general number and we go down the line, with that we are always going to get 3. It doesn't matter what X is, you always get 3, right? And so this is deductive reasoning. And again, there's no patterns that I'm using here. I'm just using mathematical rules. I'm using a general sort of proof, if you will. And that actually is going to be it on inductive and deductive reasoning. Just in recap, let me swing back up to these definitions. So deductive reasoning, we're using rules, we're using facts, we're keeping things general, we're not using a pattern. And on inductive reasoning, we're going to use patterns to figure out, you know, maybe what the next thing is in the sequence, or we're going to use patterns to say, yeah, I think this is true, and it might be, but it you know, you don't know for sure until you do deductive reasoning. So I'll leave you guys to work on the worksheet, and that'll be it for me in this lecture recording.